King is always thinking about what is the most efficient choice, the best path forward, and the right move. Most of the time, he's actually thinking about Paladins, where he plays a variety of off-brand Overwatch heroes, but occasionally he's also bringing in the same line of thinking to programming. You might remember him from his talk on locks, and when he showed off Zap, his event loop implementation. The title is Schedulers and Stuff. King, the stream is yours.
Alrighty, so yeah, as the title says, it's going to be anything, or well, not anything, but a lot of stuff related to scheduling. And so some background around me, I mostly do just optimizing stuff. That's about it. But yeah, I focus in concurrency, memory optimizations like data layout and allocation and collection, all that. And then also I/O like sockets and I guess file I/O. There's many systems related stuff. And so for the terminology, it's probably important to know what we're talking about when I say scheduling. So like a scheduler is something that controls how work is executed. So like I'll get into analogies later, but a worker is actually what executes task, and then the task itself is the work needed to be done. And so you can probably think of it like in a programming setting where there's a manager, which is the scheduler, there's the developer, which is the worker, and then the task is like a Jira task or whatever. That's probably a good analogy to use. And so there's different types of multitasking, which is how tasks like scheduled. The first would be preemptive. This is the most common for programmers to at least understand, kind of. It's basically where there's something else that's controlling when tasks start or stop instead of the tasks themselves. And so a common example is like the OS scheduler. So if your task runs too long, it's going to pause it and let something else run so it doesn't take up too much time. The benefit of this is that no bad actors can run for forever and consume all the resources, but the downside of it is that it requires resources on its own to manage them all and then stop them when necessary. So the other method of multitasking is cooperative scheduling, which is where the tasks themselves decide when to switch out. And so the scheduler just only needs to start them, and then they can have the opportunity or the responsibility to stop them or do something else. So that is generally good for throughput because tasks can go all the way for how long they want to complete instead of having to be paused, which in a preemptive scheduler, that's more optimized for latency because everything gets an equal amount of turns. But work being paused makes it so that the time it takes to complete a work gets longer. And so another two terms that people probably confuse about is concurrency and parallelism. So like concurrency is being able to sort of do multiple things, but not really. So like you're able to switch between multiple things to act like you're doing multiple things. This is mostly how I think our brains work. It's also how user interfaces are kind of, because generally they're single threaded, so but they also have different components interacting with each other. So that means you're generally using some kind of concurrency where it's doing one thing, then starting on the next component, then the other and the other. So it's like switching between them. And then parallelism is the act of actually doing two simultaneous things at the same time. So it's like one person working on something, but switching between them is concurrency. But two people working on something, each doing their own thing, is in parallel. And so concurrency enables parallelism because it allows stuff to switch. And then when stuff can switch, they can switch to another person. And what that allows is that two people can work on two different things or the same thing. So in a scheduler, there's an idea of a run queue. So there's a running task, which is like the work actually being currently performed. There's a worker who's doing the work. And then there's a queue of other tasks waiting for their chance to be worked on. Like a common example of this is in grocery stores. like there's a checkout line, people waiting for checkout are the task. When the person who is actually doing the checkout, like, is paying for stuff, is a currently running task, and then thus cashiers, like the worker. And so all you need for a scheduler is basically just one function, which is schedule. Well, all you need for a cooperative scheduler, because that's what we're going to be focused on. So all schedule does in this case is puts some task onto the run queue. Whether that's in front of it or that's the last of it, that's like a schedule by scheduler basis. But we're just going to assume at the end because FIFO is generally the order once you think about stuff. At least I've come to assume. And so the complicated bit is how this interacts with Zig async. So this is just my representation of async, at least how I learned to reason about it. It might differ, but I'll just walk through it either way. There's a lot of code to go through though. So when you do an async function call, it uses the returning variable or returning address to store the actual frame itself. And then it just starts the frame and runs until the first suspension point. So that's what it's conceptually equivalent to. And so when you await, it's kind of similar where you're just waiting for the result by checking if it's done. And if it's not done, then you suspend and have it call you when it is done. So everything async and Zig is more completion based over polling, like it is in something like Rust or I don't know, maybe JS, where they use like iterators or pollers features. When it's here, you just tell what you want, and then something will eventually resolve that instead of when it's ready. And so one tricky little aspect of this is that in order to return values, the scheduler has to insert some code right at the end of the function to check for any awaiters. And if there are, then it resumes them. So that little bit is not actually triggered by anything code-wise. So it's a bit hard to understand extra memory accesses if you look at a code gen or if you're doing like frame resource handling. And so that showcase async await, which you suspend and resume. And so we have to explain what suspend and resume do. So when Zig is compiling an async function, it generally creates a new function, and then it creates like a switch statement with all the suspend points interleaving. And so whatever data that one suspend point needs after the other is stored in a context or the frame data. And so it just ends up in like a function with a switch case and then the code for those suspension points in between all the switch cases. And so when you suspend, what you're doing is actually setting it so that the frame, when it is resumed later, will jump to the next switch case. And then it runs the code inside a suspend block. The reason that suspend has a block, because this is, I think, pretty confusing for the most part, as it's not really in other languages. The reason that suspend has its own like execution block that runs after it updates the switch case is that because, like, think of it in a multi-threaded setting where you set the switch case and then you schedule the frame to be resumed, but there's a race condition where if you schedule the frame to be resumed and then set the switch case using a suspend, then the another thread could resume it before you suspend it and set the switch case. So then you were just jumping back to the original switch case instead of jumping after the suspend block. So there's a race there. And so that's why the suspend has its own code block, which runs after it sets the switch case. So that means it's safe to be resumed inside that block. And that's when you actually schedule it to be resumed. And so resume, pretty simple. It just calls the generated function with the frame. And then that does all the switch case dispatching, gets to the right place where it's suspended and continues on. And so we can use both of these to implement some sort of spawn function. It's similar to like the go keyword in Golang. So what you start off with is making a decorator or like a wrapping async function. And what that'll do is first suspend and then schedule the frame. So this has the ability to This has the ability to effectively reschedule it or yield. So you start the frame with async call at the bottom. It reaches the first suspend point, which is the first suspend here, which will schedule a frame. And so that when it continues after that suspend point, it's been scheduled onto like the run queue. So that means it's probably in another thread or it's on the same thread, but it's running. And then, or it's running concurrently. And then you actually do the async function itself. And then you free the async memory because it was allocated. The reason there's a suspend for the free is because, remember from earlier, the compiler has to insert some extra code at the end of an async function to resume anything that's awaiting it. But if you're about to free the frame, you don't want to touch the memory after, because when it checks for awaiters, it has to check the frame and it dereferences it. So if you were to just free it and then return, it's going to free it and then try to resume an awaiter, and that's going to segfault. So you suspend to make sure that after that, it's not going to actually touch any of the frame, and then you do the actual freeing of the memory. So I think there's already an example of this in the current event loop in the standard library. Basically, I think it's called run detached. It implements this. So if you want like a concrete code example, it's probably best to go there. And so now we get into the multi-threaded part. The reason you'd probably want multi-threaded is just to be able to increase throughput, because the original single-threaded queue was only one worker, and so that worker can only run one task at a time. And if there's a lot of tasks to run, that's going to take a longer time, I think, linearly. So what you want to do is get through the most tasks as possible. And so like the intuitive next step to that is just to add more workers to the same task queue though. So this seems like a good idea because there's just more workers. So wouldn't it make sense that the line will get depleted faster? It does make sense, but not in the context of computers, because as you can see, they're all going to the same task queue, and that needs to be synchronized. And heavy synchronization, or multiple workers racing on the same resource, is what makes things slow in the land of CPUs. So in order to handle that contention, there's a few things we can do. And the idea behind it is just to decrease the amount of stuff people or two workers are trying to do at the same time that's shared between them. So we could have per local run queues for workers. So like each worker has its own queue, and they only check there first, and if that's done, then they can check elsewhere. But if they're checking their own queue, that generally means that other people are checking their own, so they don't have to share the same queue and race with each other. Another option we could do is reduce the amount of synchronization on the run queues themselves. This gets into the lock-free programming, which is its own topic, and probably can do a talk for that later. Wink, wink. But the last option is to reduce locking on the idle worker queue. So in addition to a run queue, which is all the tasks that needs to be run, there's also a queue of workers who don't have tasks to be run. And so when a new task comes in, it has to look for a worker to actually process it, use that, or it just puts it in a queue. So those are both places for synchronization, because multiple workers can be checking if there's any other workers that need to do work. And so if there's multiple checking, there's multiple synchronization. And so you can reduce that. And so what happens when a worker runs out of work? Like I said earlier, it just goes into an idle work queue. But if there is, like, what does it do in the idle work queue? And I think there's two ways of resolving, or I guess, what does it do before going into idle work queue? And so one way is to ask another worker for work. This is like something that makes sense, but also something that is probably very inefficient for general workloads. So what this means is that when it runs out of work, it has to ask another thread to schedule it. when work comes by. And that process requires waiting for the other worker to acknowledge that request and then waiting for them to complete whatever task they're doing in order to wake you up. So there's a delay there, and it only really works if the task that's being performed is like really short. There's less of a delay of them just working on a task than to see your message. But the upside of it is that you don't have to synchronize your own run queues, and I'll explain why you have to do that for the other option in a bit. But the synchronization, as I noted earlier, is pretty expensive, so less synchronization is generally better. The other option is to just steal work from them without their acknowledgement. So this has the effect of balancing work across all the workers without them having to interact with each other, because again, that would be slow. But it also means that they have to, every time they go to check their own local run queue, it has to be synchronized with others because others can be stealing at the same time. So it's generally more synchronization. But for modern processors, that seems to be like a decent trade-off for performance. And so this is what it would look like in a shopping setting where there's multiple workers and each have their own queue, and then tasks can go between workers if they want, which is like the work stealing. And so this is a type of thing that you actually see in grocery stores where there's multiple checkout lines and then each have their own line and people can move between them back and forth. So it's not something that's only unique to programming. It also appears in like real world scheduling in general. Or like if you're working on a programming job, you just look at the board for your task and then you just pick one without having to reconcile with other programmers. Another form of work stealing. And so now we can get into the thing I'm working on, which is called Zap. So Zap is a multi-threaded work stealing general purpose task scheduler. And it's written in a way that tries to not have heap allocations, not have locks, and it's mostly like throughput oriented. So like it's good as a thread pool. It's basically just a thread pool. Yeah, it's just a thread pool, but fast. And so I'll get into the points of those little asterisks on a no heap and the no locks. Basically, for the no heap is that all the memory that it uses is passed in by the user. So whether that's allocated in global space or on a heap or on a stack, it's up to them. So it doesn't require heap allocations. And for the lock or the no locks is it implements its own wait queue, which is basically what mutexes are or locks are. But that's why I put a little asterisk there, because is it really no locks if you're implementing a lock kind of ish? So it's up to you to decide. But there's no obstruction um, algorithms. That's a concept for lock free and wait free and all that. So that helps in scalability. Before I introduce the design of Zap, we can do a little demo of all the different types of run queues I've noted from before. So I have the code for this. I implemented a quicksort, a multi-threaded quicksort, which is like a fork join pattern. So there's the partitioning, and then there's two frames, each to handle the low side of the queue and then the high end of the array, queue and array. And so then it joins them all together at the end using a wait. So it's a basic fork join kind of pattern. And then there's three schedulers that implemented for it. One is the single threaded work queue from earlier, which is just as one thread and one work queue. We can actually go into the code of it, and it's pretty simple. I think a few lines of code. Basically, it pushes to a run queue, which is a list or a linked list in this case, and just keeps popping them and resuming or doing the work or running the task. And so anytime we want to reschedule, we just stop the current task and then put it into the run queue so that it can eventually complete or continue after this spend. And so this is a single threaded case. It's pretty simple. There's also the multi-threaded case, which is the single run queue but multiple workers from earlier. And then here's the implementation for that. And then I also added a Zap-based version of it, which has its own monolith of code, which is the Zap code base, which I'll explain in a little bit. But we can benchmark them now. So like, here's the baseline, which is the single-threaded performance. So this is how it's scheduling tasks on a single thread. And then we have the threaded version, which is the shared run queue, but with multiple workers. And as you can see, even though we're actually using multiple threads here, it's actually kind of slower because that's mainly due to the cost of synchronizing on that shared run queue. So all the operations have to go through the same lock. And the cost of putting threads to sleep and waking them up and then coordinating all of that can get really expensive. But if you use the Zap approach, which is every worker has its own queue and only checks outside when it needs to, this can greatly improve the throughput because there's less synchronization. So we get the benefit of multiple threads without the drawback of all the synchronization that generally goes along with it. And so we can now look at why Zap is so fast. So there's like, I think, three main concepts in Zap. It's the task queues, which hold all the tasks that need to be run. So for each worker, it has its own little bounded queue of tasks, meaning it's limited, like a ring buffer, where the worker can push tasks to it and pop them, and then others can steal tasks from it. So like work stealing. It also has an unbounded queue, which is for when the bounded queue overflows, since it's a limited capacity. So when that's filled, then it goes to a separate queue, which is based on Dmitry Vyukov's MPMC or MPSC, which is an intrusive linked list based queue. So given it's a linked list, then it can hold as many tasks as it needs without memory allocation. And to manage the workers themselves, there's an active queue. So the job of the active queue is just to hold a reference to all the currently working workers. And given it's a queue, it means that it's actually a stack consisting of all the workers intrusively provided. So they don't have to, none of this requires heap allocation. The workers themselves are allocated on the workers thread stack. So that's a way to avoid having to heap allocate stuff. And so all the workers that are currently running go in active queue. And that's used to find other workers to steal. That's also used to synchronize shutting them all down. So because it has access to all of them. There's also the idle queue. It's where workers go when they saw that there's no work to perform. So they just go in a stack. And then when there is work to perform, then it pops from that stack and then tries to find the next worker to work on tasks. And then there's the worker manager. I think this is the more innovative part of Zap, whereas the rest was just taking existing algorithms like the Triber stack or Dimitri's queue or the queue and Go, the ring buffer and Golang, and just putting them all together. I think this one took an actual effort into designing. Exists something similar in Tokyo, I believe, but not to the same extent because it still uses locks. So basically, there's one 32-bit integer that's accessed atomically using compare and swaps. So each state transition is done atomically, and there's no locks for synchronization, and there's no interruption. So it has the amount of idle workers encoded inside the bits, as well as the amount of spawn workers. So the added workers is to keep track of if there's anything to resume, and then the spawned workers is to keep track of how many active workers there are, as well as if it should spawn a new thread or if it just should resume an idle thread. And so putting them all in the same integer means that anytime it wants to start a new thread, it just has to load the atomic, which is really cheap. You just load and look at the amount of workers, and if something is already spawned or if there's nothing that can spawn, then it just gives up there instead of having to acquire a lock, then check, and then release it and have a bunch of those acquiring, checking, and releasing all the time, which is going to slow it down. So there's also the state at the end. So the state is basically a way to throttle the amount of workers that are starting and stopping, which is it acts as a way to decrease synchronization. Yeah. And how it does that, it means it uses basically the concept of a waking worker. So I'll explain that. There's always only one worker that's in the state of waking at a given point. And if that worker finds work, then it makes another worker waking so it can find work. But if it didn't find work, then it just goes back to sleep. And so, given that there can only be one worker waking at the same time, or at a given point in time, it means that there's only one worker that's being woken up, which is the expensive operation from the work requesting type of distribution. What that prevents is all the workers trying to wake up to try and race on the same run queues and try and steal from each other, which is bad. And what it also prevents is workers checking for the run queues, seeing that they're empty, but they're really in the process of being filled, and then going to sleep and never actually having solved that it was filled up. So there's two states at the bottom called waking notified and suspend notified. Basically, waking notified means that there's currently a worker that's looking for tasks, but he hasn't found one yet. So if he goes to sleep, make sure he wakes back up because we create a new task. And then suspend notify is basically the same thing, but for when there's no waking workers. So those effectively make sure that when a worker tries to look for work and fails to, that it doesn't miss a notification to wake up. And so that's the main algorithm of Zap. All the code, as usual, is available on the GitHub. I have a few branches, a lot of branches in that repo, but the main ones are the Showtime branch, which contains the serial threaded and Zap workload I showed earlier. You can check out if you want to just see how schedulers work and understand the different stages of them. There's the branch that makes Zap usable as a Zig library, so if you actually want to use Zap and start playing around with it. And then there's the Tombstone branch, which contains all my failed attempts at writing schedulers. So if you find that valuable or you want to learn from that, go ahead. But hopefully you learned that it's all just a bunch of queues doing scheduling and stuff. Yeah.
Wow. Thank you, King. That was a very nice way of ending the presentation. Okay, let's switch to the Q&A view then. Whoa. Okay. First of all, I think I should say thank you for actually talking about async await and explaining how async await works in Z. There's been a lot of people asking about this stuff. I didn't have the courage of tackling the subject directly yet, so I've been searching.
I just think that's my case. Like I remember you talking about not using that way of reasoning about it, so I'm not sure if that really resonated with other people.
That's a good question. So I think that there is space for everything. Like the same way that maybe I am right, and some people might might need something different to have the light bulb turn on in their head. But I'm sure that there's other people that prefer that kind of explanation, and you probably just show them precisely what they needed to see. So I guess we'll see what the feedback is. But in any case, there's without any shadow of doubt space for multiple different explanations and way of. Yeah. So well, that was awesome. Thank you. Let's see what what questions people have. So by the way, if anybody has a question for Kim, please type it down in Twitch chat or Discord or IRC if you're in the Zig channel. I'm not in the Zig channel. Why am I not in the Zig channel? Why is my client not connecting? Okay, maybe IRC is is out today for me. But yeah, and please try to tag me in the question so that I don't miss it. In the meantime, King, I have a question for you. So, and please correct me if I'm saying something wrong. But I'm not a huge Rust expert. I'm not a Rust expert at all, but I watched recently the talks that they had out there on async awaits because I was trying to research what to do in our case, and I wanted to see what others had put out in the meantime. So I saw a couple of presentations about async await, and I saw that in Rust they make a pretty big distinction between and again, correct me if I'm using the wrong terminology, my might be to remember, but I think they have a executor and a reactor, right?
Yeah.
Yeah. So the executor is supposed to be the component that schedules tasks, while the reactor is a component that is supposed to basically react to I/O notifications and stuff like that. So here's my question: they make this distinction between these two sub problems, let's say, while in our case in the Z community we always talk about the event loop, which is this thing that is supposed to kind of do both juggle tasks, but also we say that it's the event loop that integrates with whatever notification API or whatever. So my question for you is, do you think the Rust distinction between these two things would be valuable for us? Do you think, are we going to give up some form of performance by trying to divide the problem into two separate sub-problems?
Yes. So in Rust, the executor, it goes both as basically a thread pool, but sometimes people use it to reference an executor which supports a reactor internally. So I think that's kind of what the Zig current event loop is trying to be.
Mm-hmm.
As for the distinction, I currently make that distinction inside Zap. So like if you go on the Showtime branch right now, the Zap code is actually under a file called executor, because right now it's just a thread pool. But the distinction is pretty useful because it lets you use different APIs for different parts of the scheduler. So like APIs that only work with threads can sometimes be more efficient than APIs that have to block threads using IO or something like that. But it's also a double-edged sword because having to block on a thread, then block on an IO on another reactor component, it's kind of actually slower because you're doing two syscalls. So there's benefit to actually like incorporating the two. And so having the scheduler be powered by the same driver-ish thing that the reactor is powered by, and then integrate them together, that can reduce the amount of actual syscalls being performed, which I haven't played around with, but I'm guessing that can increase performance. So I'll have to try it out eventually.
Okay. So in other words, then you, if I remember correctly, also from your presentation, you then aim for Zap to eventually become both, right? Because you want to cover IO stuff. Mm-hmm.
I want to add like IO timers, eventually like signals and process stuff, the whole deal.
Okay. Yeah, okay, that makes sense. Yeah, I was curious because we don't have this terminology anywhere around, and who knows, maybe this is something that is good to steal. Okay, let's see. I think we have a couple of questions already. One is from Felix. King, will you provide doodles for the official Zig documentation explaining concepts?
Maybe if you want some. I don't know if these doodles are good though. They're like things that I drew up in like some web view thing. Just pasted them in.
Yeah. King, I think people love your doodles, you know?
Really?
You have to accept this fact, yeah.
I don't think they're like up to quality. I want like someone really good at art to try and make one to see what it turns out into.
Oh, okay. So somebody trying to polish your concept.
Yeah,
Mm-hmm.
like the polish.
Yeah. Well, honestly, I think that the handmade quality to them is part of the appeal, at least for me. And I think like I, I think this is so prominent in your design that people don't care about the slightly different background color and the dots. Like when I did a blog post, for example, I didn't clean your doodles up in any way. I just put them there as they were, and nobody complained. I think I only saw, I genuinely only saw positive comments. I swear, if I saw a single negative comment about it, I would tell you. But I didn't. People love them.
Uh-oh. What happened there?
Okay, so we have a question from Andrew. Is using atomic load store compare and swap problematic, or only actual contention on lock?
The problematic bit is there's two problematic bits actually. The first is when two CPUs try to CAS or compare and swap at the same time. The one that fails has to go back into memory to fetch the new value again. And so that part is the slow part, actually going back into memory and then having to synchronize all the caches of the CPUs that are trying to CAS at the same time. So, like, if you have a atomic swap and there's like 128 cores doing the same atomic swap on the same memory, you can probably have delays of like in the order of milliseconds just for that single instruction. So, yeah, there's cost in atomics, but there's other cost in putting a thread to sleep. So, like in a lock's case, if you have a spin lock and the work completes really quickly, it doesn't have to put the thread to sleep. So that can actually be faster than doing a bunch of atomics where they're contending again. But if the thread that's doing work gets put to sleep, that means others have to wait, and then the process of waiting is actually the slow part because it's this call, and that takes like a few microseconds. So there's two like competing overheads for locking, whereas in atomics is just one, and there's ways to kind of mitigate that.
Mm-hmm. So Andrew has a follow-up question then. Yeah, is it free to do a compare and swap if there is no contention? Quote unquote free.
For modern CPUs, basically. So like a compare and swap without contention on my current Zen Plus CPU is like 10 nanoseconds. An atomic store is like 1 or 2. So yeah, it's a cost of a few memory instructions. So it's basically free. The only expensive part is just when more people start trying to do the same thing on the same memory.
Okay. So King, are you ready for benchmarking Zap on yet another platform?
I am. I think Hayes had a M1. I don't know if he ran Zap on it, but I'm pretty curious to see how it's gonna perform there.
Yeah, I think there are also some differences between the TTKs. Oh no, but Hayes has an actual Air, I think, or no, he got a 13-inch MacBook Pro. So yeah, yeah.
Pro. So you got the Air.
Oh, he got the Air. I'm not sure actually.
I don't know which one.
No, I think he
I
got
know
the
he
Pro.
spent a lot of money on it. That's all I know.
Yeah. Okay, so well, I'll be able to help too soon, hopefully, and not just me, but also a few people more. So yeah, looking forward to benchmark Zap. Oh yeah, also Jacob in chat is ready to bench
Yeah.
Zap for you.
Everyone is a CI. More CIs, please.
Okay, let me double check if I missed any question anywhere too, but I don't see any other mention of me, so I think we're good. Is there anything else, King, you want to say before we move forward?
Check out Zap. Try and use it. I need more real life examples because all I have are really benchmarks. So it'd be nice if people started playing around with it, see what's broken, see what they want out of it, that sort of deal.
Right. That's making a lot of sense. And we need to progressively start also trying to incorporate async await in the programs that we make. And I swear, by the way, thank you for this talk. I think this was a nice addition to the available materials on async await. And I swear I will also add more to the list in the near future. I just need to be done with the website first.
More students later.
Yeah. So thank you again, King.